Hey everyone! In this video, I'm going to give you an introduction to recursion. So in computer science, recursion is a way of solving a problem by having a function call itself. To see how that works exactly, let's take a look at a few examples here. First of all, let's think about factorials. And let's just quickly review factorials here. If you're given a positive integer n factorial is equal to n times n minus 1 times n minus 2 times and so on down to 3 times 2 times 1. So I'm just going to give you a few examples here. 4 factorial is equal to 4 times 3 times 2 times 1, which is equal to 24. And 2 factorial is equal to 2 times 1, which is 2. And 1 factorial is 1. And what about 0 factorial? It's actually defined to be 1. And you might say, why is that? But basically that's just how it's defined. And let's just say here, we're trying to write a function called, let's say, fact, which takes a positive integer, or 0, as its argument, and returns the nth factorial. And let's say we want to write this function using recursion. How can we do that? To solve this problem, or to write this function recursively, we need to actually examine this equation in a little bit more detail. Okay, so I brought that equation over here, and like we saw earlier, we had n factorial being equal to n times n minus 1 times n minus 2, and so on, times 3 times 2 times 1. And when you see this equation, and when you look at this part following the first n, you might notice that this part is equivalent to n minus 1 factorial. And that might be more obvious if I write it separately here, as n minus 1 factorial equals n minus 1 times n minus 2 times and so on, times 3 times 2 times 1. So this whole thing is equivalent to this part. So you might say, well, we can rewrite n factorial as n times n minus 1 factorial. And that's good. This new equation is mostly correct, but it's not a complete definition of factorials. Let's see why. Let's say if you plug in 2 to n right here, it works just fine because you'll get 2 factorial being equal to 2 times 2 minus 1 factorial, which is 1 factorial. And 1 factorial is 1, so 2 times 1 factorial is 2, and that's correct. What if you plug in 1 here? It's still good, because you'll get 1 factorial being equal to 1 times 1 minus 1 factorial, which is 0 factorial. And 0 factorial is 1, as we saw earlier. So that's 1. And this is correct. But as soon as you plug in 0 here, it breaks. Let's see how that works. 0 factorial is equal to 0, here, right here, times 0 minus 1 factorial, which is minus 1 factorial. And minus 1 factorial is not defined. So this definition works only for n that is greater than or equal to 1, but it doesn't work for 0. So actually, for this definition to be complete for factorials, we need to write n factorial as 2 separate cases. So here we're going to write n factorial is equal to n times n minus 1 factorial if n is greater than or equal to 1. And if that's not the case, or if n is equal to 0, I wrote otherwise here, n factorial is equal to 1. And this is actually a complete definition of all factorials for all positive integers and 0. So let's just quickly see how we can use this new definition of factorials to find the factorial of any positive integer, let's say 3. So if you ask yourself, what's 3 factorial? There are 2 ways of answering that question. The first one would be to use the old definition, and then the second way would be to use this new definition. And let's use this new definition here, because we're going to use this new definition later to write a function using recursion as well. So using this definition, we can ask ourselves, what's 3 factorial? Well, 3 is greater than or equal to 1. So by definition, this is equal to 3 times 3 minus 1 factorial, which is 2 factorial. And then we can ask ourselves, what's 2 factorial? By definition, since 2 is still greater than or equal to 1, it's equal to 2 times 1 factorial, And then we can do the same thing for 1. What's 1 factorial? Well, it's 1 times 0 factorial. And then as soon as we have this, we'll know that 0 factorial is 1 by definition. And as soon as you have that, you can plug 1 to 0 factorial here, and then you'll know that 1 factorial is equal to 1 times 1, which is 1. And then you can plug that back in here, and then you say, okay, 2 factorial is 2 times 1, which is 2. So we can plug that back in here. And then we'll say 3 factorial is 3 times 2 factorial, which is 2. So the answer here is 3 factorial is 3 times 2, which is 6. Okay, now this whole process might seem a little bit silly, but this kind of thinking is going to be actually the basis for implementing the function we wanted to implement earlier recursively, fact of n. And fact of n, as I said earlier, is going to take n, which is either a positive integer or 0, and it's going to return n factorial. So let's see how we can implement it using recursion. And actually, all you need to do for that is you need to translate this new definition of factorials into code. So let's just bring this definition up here. So like we saw earlier, n factorial is equal to n times n minus 1 factorial if n is greater than or equal to 1, and then it's 1 otherwise, or if n is equal to 0. And then we're going to translate this definition directly into code, and I'm going to use Java here just as an example. And like we saw earlier, we're trying to write a function called fact, which is going to take n, an integer, and it's going to return an integer, which is going to be n factorial. And just for simplicity here, I'm going to assume that the given n is always positive or 0, so it's never negative. And to write the rest of the function, it's pretty simple. We just need to translate this formal definition into code. So here it says n factorial is equal to n times n minus 1 factorial if n is greater than or equal to 1. And what we're going to return from this function is going to be the value of n factorial. So here we just need to write if n is greater than or equal to 1, we're going to return n times fact of n minus 1. So this is the same as saying the value of factorial n is going to be n times factorial of n minus 1 if n is greater than or equal to 1. And then we're going to write otherwise or else. That's when n is equal to 0. We're just going to return 1 because we know that that's the value of 0 factorial. So as you can see, this is a recursive function because this calls itself, fact calls itself right here to solve the problem of finding n factorial. Okay, this function seems pretty simple, but does it actually work? Well, it does. To see how, let's take a look at a few examples here. If you have fact of 0, I just wrote it as f of 0. That's pretty easy because here we get this line right here because 0 is not greater than or equal to 1. So we're just going to return 1, which is correct because 1 is 0 factorial. And what if you're given 1 as n? Then I'm just going to write f of 1 here to stand for fact of 1. When this is called, it's going to hit this line right here because n is equal to 1. And then it's going to try to return 1 times fact of 1 minus 1, which is 0. So f of 0 here. And then when f of 0 is called, it's going to go to this right here that we saw earlier. And then f of 0 will say, okay, my value is 1. So this is going to return 1. And then in f of 1, it's going to say, okay, what I'm going to return is 1 times the value of fact of 0, which is 1. So we're going to return 1 times 1, which is 1. So that's the correct answer. Okay, to help you understand this a little bit better, I'm going to give you another example here. Let's say fact of 4 is called. I'm just going to write f of 4 here. And when it's called, we go to this line right here. And since n, which is 4, is greater than or equal to 1, it's going to say what I want to return from that function is 4 times fact of 3. But we don't know what the value of fact of 3 should be, so we need to call that function. So I just wrote it here. Here I'm saying the value of f of 4, the return value of f of 4 will be 4 times f of 3. And then we need to call f of 3 to find the return value for that. And once we call f of 3, the same thing will happen. The return value of f of 3 will be 3 times f of 2, whatever the return value of f of 2 is. So we'll call f of 2, or fact of 2. And then we'll say, okay, that's 2 times f of 1. Actually, there's a typo here. Whatever the return value of f of 1 is. So we'll call f of 1, and then f of 1 is 1 times f of 0. And then as soon as we call f of 0, we go to this line like we saw earlier. So we'll just return 1 from that. Once we return 1 from f of 0, we'll go back to this call, f of 1, and then we'll say, okay, we wanted to return 1 times f of 0, and we now know the value of f of 0, which is 1, so we'll just say we're going to return 1 times 1, which is 1, from this function. And then we'll go back to this call, where n was 2, and we wanted to return 2 times f of 1, whatever the return value of f of 1 was, and that turns out to be 1, so we'll return 2 times 1, which is 2 from this function. And then we'll just basically keep doing that. F of 3 wanted to return 3 times f of 2, and f of 2 happens to be 2 here, so we'll return 6 right here, and then we'll go back here, the original call that we made, and then f of 3 turns out to be 6, so we'll say, okay, f of 4, we wanted to return 4 times whatever the return value of f of 3, which turns out to be 6, so we'll return 24 from this function, which is correct. And this wraps up this section about factorials. Let me know in a comment below if anything was unclear. Okay, now to better understand recursion, let's take a look at another example here, the Fibonacci sequence. So I already talked about this in one of my previous videos, but the Fibonacci sequence is a sequence of numbers that starts with 2 ones at the beginning, and the numbers after that are generated by adding up the 2 previous numbers. So for example, the third number is 2 because 1 plus 1 equals 2, and then the fourth number is 3 because 1 plus 2 equals 3, and so on, and then it just keeps on going forever. And given this sequence, let's just say that we're trying to solve the problem of writing a function, let's say fib, which takes a positive integer n and returns the nth number in this sequence, the nth Fibonacci number. So if you're given 3 as n in this function, you should be able to find and return the third Fibonacci number, which is 2. And if you're given 4 as n, you want to be able to find and return the fourth Fibonacci number, which is 3 right here. Now, if you want to try solving this problem yourself, pause the video right here and post your solution in a comment below if you want to share it with others. Now, to solve this problem using recursion, you need to first formally define the relation between different Fibonacci numbers, just like we did with factorials. So for that, we're going to write fn equals fn minus 1 plus fn minus 2. So I'm denoting the nth Fibonacci number as fn, and this is saying the nth Fibonacci number should be the sum of the 2 previous Fibonacci numbers. So an example here would be this one right here, f5 equals f4 plus f3. So this is saying the 5th Fibonacci number, f5 right here, should be the sum of the 4th Fibonacci number, this one right here, plus f3, which is this one right here. So just like we saw in the case of factorials, this equation is correct most of the time, but it's not complete. So if you plug in 5 to n, it's correct. This equation is still correct. But as soon as you plug in 2 to n, you get f2 equals f1 plus f0. And here I didn't define f0, 0th Fibonacci number, I guess. So this equation just breaks. And it's the same thing. If we plug in 1 here, we have f1 equals f0 plus f minus 1. f1 is the first Fibonacci number, and f minus 1 is not defined. So this equation doesn't work for n equals 1 either. And to fix this equation, we need to actually rewrite it as 2 parts. The first part is going to be just like we saw, fn equals fn minus 1 plus fn minus 2 if n is greater than or equal to 3. And then the second part will be fn is equal to 1 otherwise. And that's when n is equal to 1 or 2. Now, to solve the problem we saw earlier of writing a function called fib, we just need to translate this formal definition into code. Let's see how we can do that. I just wrote here int fib int n, and this just means we're going to define a function called fib, which is going to return an integer, and then it's going to take n, which is an integer, as an argument. And then inside this function, I'm just going to first of all assume that the given n is a positive integer just for simplicity. And then after that, I'll say if n is greater than or equal to 3, then return the sum of the two previous Fibonacci numbers, fib of n minus 1 and fib of n minus 2. And otherwise, n is equal to 1 or 2, so we're just going to return from this function. Okay, let's now take a look at a few examples here to see how this function works exactly. I'm just going to move this function over here. Okay, first of all, let's say this function fib is called with 3 as the argument. Then what happens is we go to this line right here. 3 is greater than or equal to 3. So we'll say, okay, the return value of fib of 3 should be the sum of fib of 1 and fib of 2. So that's what I wrote here. Fib of 3 should be the sum of fib of 2 and fib of 1. And then in fib of 2, we'll go to this line right here because 2 is not greater than or equal to 3. So we'll return 1 from fib of 2. And just like that, we're going to return 1 from fib of 1 as well. And once we have these two numbers, fib of 2 will go in here, and fib of 1 will go in here. So 1 will go in here, and then 1 will go in here. So we're going to return 1 plus 1, and we're going to return 2 from our function. And that's the correct answer. By the way, just quickly about terminology. In a function that uses recursion, or in a recursive function, the condition where it doesn't call itself at all, but instead returns, for example, just a number is called a base case. And then the condition where it calls itself is called a recursive case. So in this example, when n is greater than or equal to 3, that's a recursive case. And otherwise, that's a base case. Okay, let's take a look at another example here. Let's say this function fib is called 4 as the argument. That's this one right here. Then it goes to this line right here because n, which is 4, is greater than or equal to 3. So we want to return fib of 3 plus fib of 2 as the return value of fib of 4. So that's what I wrote here. The return value of fib of 4 should be the sum of the return value of fib of 3 and the return value for fib of 2. And when we hit that line right here, we don't know what the return value should be for fib of 3 yet, so we'll need to call it separately. And then the same thing will happen. We'll say, okay, whatever we return from fib of 3, that should be the sum of fib of 2 and fib of 1. So we'll call fib of 2, and then we'll say, okay, the return value for fib of 2 should be 1, because 2 is not greater than or equal to 3. So we'll go to this line right here, and then we'll return 1 from fib of 2. And then 1 will go in here. And then at this point, we'll know that we should return 1 plus fib of 1 from fib of 3. And so we're going to call fib of 1. And then it's the same thing. We'll return 1 from fib of 1. And then 1 will go in here. And then we'll say, okay, we should return 1 plus 1, which is 2 from fib of 3. So we'll plug in 2 right here. And then we'll say, okay, we should return 2 plus fib of 2 from fib of 4. But we don't know what the value for fib of 2 should be. So we're going to call that. And then again, we'll say, okay, we should return 1 from fib of 2. So 1 will go in here. And then we have 1 for fib of 2 and 2 for fib of 3 at this point. So we're going to return 2 plus 1 from fib of 4, which is 3. And that's the correct answer because that's the fourth Fibonacci number. Okay, so that's one way to implement this function fib. But here you might notice that it's not the most efficient way to do it. To see why it's not the most efficient way to do it and to see how you can fix it, you can just check my video about dynamic programming. Okay, and this was number 6 of my data structures and algorithms series. You can find the entire series in the description below. And to close things off here, let me give you another practice problem for recursion, which comes from this video's sponsor, Brilliant.org. In this problem, there's a frog looking over a river which is 11 feet wide, and there are 10 stones placed in this river 1 foot apart. So from the end of the river, the beginning of the river, I guess, to the first stone, that's 1 foot, and then to the next stone, that's 1 foot, and so on. And then from the last stone to the end of the river, that's 1 foot as well. And then this frog is able to jump either over 1 foot or 2 feet. So the first step this frog could make is either to this stone right here or this stone over here. And if the frog decides to go to this stone, then it can jump to this stone or to this stone over here. And the question here is, how many ways are there for this frog to jump from this side of the river to that side of the river? And note that this frog can never go backwards. And a simpler version of this problem would be this one right here, where there's a frog on one side of the river, just like before, but instead of 11 feet, this time the river is only 2 feet, and there's only 1 stone placed. So in this example, there are only 2 ways for this frog to go from this side to that side, because the first way would be to jump directly from this side to that side, and then the second way would be to jump to the stone and then to that side of the river. So see if you can solve the same problem for the case where the river is 11 feet wide instead of 2 feet wide. And actually the solution is pretty interesting, and it involves using recursion. Now, Brilliant is a website where you can practice your problem solving abilities with interesting problems like these, and that's really the best way to learn. So if you want more interesting problems about data structures, just go to brilliant.org/csdojo and maybe check out their Computer Science Fundamentals course. There, you'll be able to find more interesting problems about topics like algorithms, recursion, stack and queues, and so on. And there, you'll be able to find the solution to the frog problem as well. Okay, thanks for watching this video, and I'll see you in the next one.